Welcome back! In the last video, we built our first fraud detection models, logistic regression, random forest, and neural networks. Our best model, random forest, achieved an F1 score of 85%. We have been treating all errors equally. In the real world, missing a $10,000 fraud costs way more than a false alarm. So today we are taking it to the next level. Um, this tutorial will cover four key areas. Cost sensitive approach. We're going to talk about different costs for different errors, advanced models like XGBoost, LightGBM, and then business metrics, and also comprehensive evaluation of different models. Now let's import our libraries. So just notice we're importing XGBoost and LightGBM, two gradient boosting libraries that are industry standards. We're also importing cross-validation tools and multiple metrics. Now let's look at our actual business cost. This is the business cost class. Let me show you the code and explain what it does. So we are creating a class to hold our business cost, thinking of it as a container for our cost parameters. So you may ask like why we pick those specific numbers. So $200 for fraud cost. This is the average amount lost when we miss a fraud. And then $10 for false positive cost. When we running flag a normal transaction, the customer gets annoyed, the support has to call them. So that's like the cost for that. And then $30 investigation cost. Every time we flag something as fraud, a human analyst has to review. So that also costs money. So the key insight here is so missing a fraud $200 is 20 times more expensive than a false alarm $10. This is why we just can't optimize it for accuracy. So now let's look at how we calculate the total cost. So here we actually look at capture the true negatives, false positive, false negatives, and true positive. We also did calculate the fraud loss. So like FN is the false negative, it means the frauds we missed, and then each missed fraud is cost how much times the fraud cost, and then fraud alarm cost, also investigation cost. Then the total cost will be sum of all of them up. Now let's visualize the cost. So first one is the cost comparison bar chart. So we see the false positive and false negative. So, and then plot two is about the cost benefit analysis over different detection rates. So we simulate different scenario, catching 0, 20, 40, 100 different frauds. Assume we have 5 false alarm for each fraud car, and then calculate the value prevented versus costs, and then plot them to find this plus the thing. So the green line shows net benefits. So where we maximize the profits. So why does this matter? Because a model with 80% F1 that catches expensive fraud might be better than a model with 85% of F1 that catches cheap one. Okay, now let's load the data and prepare it. So first we load our data set, and then we print out the basic statistics. So we have 284,000 of our transactions, and then 0.17% of fraud rate, only about 492 frauds. So now the important part is how we calculate the class weights. So the normal transaction is 50. So the fraud transaction would be 289.44. So the weight ratio is 578 to 1. So when we give this to our model, they will weight fraud examples 578 more during transaction, like 578x. So this forces the model to pay attention to the real fraud cases instead of just learning always predict normal. So now let's train and split our data. We are using stratify equal y. This ensures both train and test sets have the same fraud rate. Without this, you may get like anarchy and have maybe 0.2% fraud in train, but 0.1% in test. Also, you need a random state. This makes sure for reproducibility, so everyone who run this gets the same split. Now let's look the feature scale. So I'm using the standard scaler. That means there's a two-step involved: feed training, feed transform training data, and then we just transform our testing data. So it basically calculates mean and standard deviation from training data, then scale it, then use the same mean and standard deviation from training to scale test data. Um, so why not feed on the test data too? It's because that would be data leakage. The test set should be completely unseen. Then we create a validation split for early stopping. So what this gave us, like we did a 20% for testing. Um, so for early state stopping, we will train XGBoost. For example, we can use XGBoost and then watch validation performance. So if stops improving, it will stop training. So this prevents overfitting. And here's the results. So we have training data set, we have test sets, we also have validation sets here too. Now let's training our model. Okay, yes, keep going. Let's just go talk with. Okay, now let's talk about XGBoost. Before we dive into the code, let me explain what makes the XGBoost special. So first, what is a gradient boosting? So remember, random forest builds many trees in parallel or bagging. Gradient boosting is different. It builds the trees sequentially. Like it builds first tree, then from the data, and then the second tree is then from the mistakes of the first tree, then the third tree will be learned from the mistakes of the first two trees, and so on. So each tree tries to correct the errors of the previous trees. This is why boosting often performs outperforms of bagging. So XGBoost, so it's a gradient boosting tree. Is the so it's used of parallel processing and the hardware optimization, so it's kind of fast. Also, it builds in like L1, L2 regularization, prevents overfitting. It also learns like the best way to handle missing data, missing values. Um, also you can like add early dropping, so automatic stops when performance not improving. It calls called extreme because it pushes gradient boosting to the extreme with optimizations. So now let's try train XGBoost. So now let's break down every single parameter in the XGBoost model. So we use the XGB classifier. So we said the estimator is 1,000 samples, so maximum number of trees to build. I'm thinking like build up to 1,000 trees, but stop early if you need it. So more trees, more complex, but early stopping prevents overfitting. We said the learning rate is zero point 0.1. So that's like how much each tree contributes to the final prediction. Um, the lower learning rate, it's more needs more tree. A higher learning rate, it's more aggressive, or also might overfit. 0.1 is like good default. Maximize depth equals 6, maximize depth of each tree. So um, that means like, so deeper trees, it means more complex patterns, but also more overfitting risk. So I think 6 is good for fraud detection because it is deep enough for capture patterns. Um, Sample, I subsample 0.8. That means use 80% of data for each tree. This is like a bootstrap in random forest. So also adds the randomness. So reduce the overfitting. That also means like each tree will use or see different data. The color sample by tree 0.8 means use 80% of features for each tree, similar to random forest feature subsampling. So it prevents any single feature from dominating. So make the ensemble methods more diverse. So this is what we calculate from here for the imbalance data. Random state is for reproducibility, so same results every time. So this is the early stopping. So if validation score doesn't improve for 20 runs, then it will stop. So it prevents overfitting. Also save time, save resources. We use the log loss for evaluation. Okay, then once we have that, we just do the training, and then we're going to make the predictions. So let's see the final results. So it stopped at iteration 137 because the validation performance not improving. It doesn't need like 1,000 trees. That's why. And then we have 0.85 as the F1 score. And our CAUC is 0.98. The total cost is 6,270. The ROI is 158.4%. So consider like we set a 1,000 tree and early stopping at tree 137. That's pretty efficient. Now let's look at the LightGBM. So what makes LightGBM different is the XGBoost and LightGBM both do gradient boosting, but they grow trees differently. So for XGBoost, trees grows level by level, like building floors of a building. And then LightGBM, trees grow by splitting the best leaf at each step. So because that the LightGBM is faster and like a leaf-wise growth, so more efficient, splits best leaves first. Also, like a histogram-based algorithm, so beans continuous features, it's faster. Um, Also, it use like gradient boost, one-side sampling, focus on hot examples. So in practice, LightGBM can be 10 to 20x faster than XGBoost on large data sets. LightGBM parameter, let's explain here. Same thing, 1003. Same as XGBoost, we have 0 0.1 as learning rate, 6 max steps, and then same thing for subsamples and features. The This part is different. We're using auto calculate weights and then silent mode, so it won't show report outputs of the model. It just will show you from this we're using the calculator weight. So let's look at the light GBM's output. So light GBM stops at iteration 146. It's very close to XGBoost 137. Both models found similar optimal complexity. And with 0.857 F1 score, I think slightly higher than XGBoost. Also have a higher ROI, sorry, lower total cost. I think it's high ROI. Let me check. Yeah, a little higher. So let's compare all the model in one table, so we can see better. So this table, it is sorted by total cost. The best the lowest total cost is on the top, and then so on. So light GBM is at 6,230 total cost, and the logistic regression is almost 10x of what light GBM has. So it means almost 10x more expensive, because it generates too much alert, like almost 1,400 alerts for logistic regression, with just sorry, I have over 1,400 alerts for logistic regression, and versus 91 for night GBM. So more alerts means more investigation cost and customer frustration, because every time you flap alert, you're gonna call your customers. So now let's visualize the model comparison. I created 6 different views, like F1 score. You can see just the first one is like GBM, then the total cost by model, I precision versus recall trade-off, alert volume analysis, and cost breakdown pie chart. So the alert volume analysis, it's eye-opening. Just a regression like flags, 1,476 transactions, but 1,386 are false alarm. Like GBM flags only 91 with 10 false alarms. Now let's look at the feature important analysis. The horizontal bar chart shows the top 15 most important features average across the random forest, XGBoost, and LightGBM. So the V14 by far the most important. We also so those features the PCA transform features that capture fraud patterns. The models automatic learned which features matter most. So you also see the amounts show up in the top features, confirming that the transaction amount also is a useful signal for fraud detection. Okay, now let's look the business recommendation. Um, let's just look the output here. So this is the the analysis identify what's the best F1 score, lowers the cost, the best ROI, potential cost savings, optimization, operational impacts, and then by looking at all those metrics, we conclude that the light GBM is the best model we can use for production. Um, then we saved all our models and results for production use. So today we have learned XGBoost and LightGBM. We went from treating all errors equally to optimizing for actual business values. So in next video, we will dive into model calibration. So see you in the next video.